Today's lesson focuses on esters, and we'll also look at condensation reactions, which is a way for us to create esters. We say that esters are derivatives of carboxylic acids. So what that means is that the carboxylic acid actually will get reacted with an alcohol and will add on to the carboxylic acid and create what is called an ester. This is an ester linkage over here, and you'll recognize it because it will have a carbonyl that is coming from the carboxylic acid, and it will have an oxygen added right next door coming from an alcohol family. And then what we'll notice is that on either side of that ester linkage, we'll have R groups or maybe a hydrogen. It all just depends on what's there. Esters are kind of unique because they are nice smelling substances. So a lot of esters are synthesized and used in artificial perfumes. So where they're not extracting scents from, oftentimes it's flowers or herbs, things like that. They extract the essential oils. If you buy cheaper body sprays, or if you buy a scented candle, something like that, chances are extremely good that these ester molecules have been added in because they smell nice. They are created through a process called esterification, although we tend to just refer to it as the reaction type, which is called a condensation reaction. And like the name implies, with condensation, a water molecule gets pulled out while we create our ester molecule. And in order to create an ester molecule, you need a carboxylic acid and you must have an alcohol. This is important. Esters are functional isomers with carboxylic acids. So that means you can have the exact same formula, and then you could create out of that chemical formula ester molecules or carboxylic acid molecules. So let's go over this condensation reaction that is used to create an ester. So what we need is some type of alcohol. So I'll just create, I'll take a 2-carbon alcohol. So there are my hydrogens, and then I'm going to put my hydroxyl on this side of the molecule. I'm going to react that with some type of carboxylic acid. So the other thing I'm going to do here, again, I'm going to get the functional groups sort of end to end. So I've put the hydroxyl on the right side. I'm going to take the carboxyl group and I'm going to put it here on the left side of the molecule, and I'll do, let's just do this. Let's do methanoic acid, okay? So this is ethanol, and this is methanoic acid. And if you put these two together, you need to help them along, okay, to have a reaction. So here's my reaction arrow. I'll just make it big. I'm going to put a little triangle there, which we should all know means we have to heat it. And typically we need to add very, very strong sulfuric acid in order to break the bonds and get our ester to form. So what happens here is we take the OH off of the carboxylic acid, okay, not off of the alcohol. And the hydrogen off of the alcohol will also get removed. When this happens, we're going to create our water molecule. So I'm actually going to put the water molecule first here. Okay, so there's my water molecule that comes off. And then what is left over, so this oxygen is going to link right over to the carbonyl on the carboxylic acid. And so what we will get is the alcohol carbons right there with that oxygen and linking right over to the carboxylic acid. And we'll put all my hydrogens in. I'll just show them for effect here. So this is how you create an ester. And then we're going to notice that here is that ester linkage right there, okay? When we name the ester, the name of this ester is actually ethyl methanoate. Okay, so what we do is we put whatever came from the alcohol group first, and we write it as an alkyl group. And then whatever was attached to the carboxylic acid, we write that as the parent name, and we add the suffix of -ate. So let's practice naming some of them. So again, what we need to do is when we see the ester linkage, like we do right here, I always like splitting it in two, because then I know this portion right here came from the alcohol group and the other portion came from the carboxylic acid. And then how we name them is, dependent on which family they came from. So we're going to call this portion of the alcohol as an alkyl group. There's 1, 2, 3 carbons. So we're going to call it propyl. And then what is left with that carboxylic acid is a 2-carbon parent. So we're going to call it FN because it's all single bonded. And then we add the suffix O8 to it. Okay, so there's our suffix of O8. So it's a little bit different. And sometimes students get confused because you think that the longest chain has to be the parent, right? That's typical, not with esters. Okay, so whatever part of the molecule came from the carboxylic acid, which would be right here. And we know that because carboxylic acids have a carbonyl group. That will be my parent. And whatever came from the alcohol, which was attached to the oxygen, will be listed as an alkyl group. So this next molecule here, the alkyl group is a methyl. And then my parent is a 2-carbon. So again, it is FNO8. And then we'll look at the last one here. So again, find your ester linkage. It's right there. Split that linkage into 2. Okay, so that is how they would have joined through the condensation reaction. This part came from the alcohol. This part came from the carboxylic acid. This is a 1, 2, 3, 4, 5. So we're going to call this a pentyl. And then we have, again, a 2-carbon parent ethanoate. Let's talk about some physical properties of esters. So esters have oxygens, which means that they will be polar. And the thing with an ester is that they actually have 2 dipoles. So I'm going to take this molecule right here and I'm going to draw it out. So I have a CH3, I have a C double bonded to an O, and then I have my oxygen and I have a CH2 and then a CH3. So what will happen in any ester is that wherever those oxygens are, you're going to create a dipole. So there'll be a dipole running through that oxygen, and then there'll be another dipole running through the carbonyl. So you get 2 dipoles, which is pretty good. And typical to other oxygen-based groups, if your nonpolar parts get really big, okay, it's going to start to act more nonpolar than it will polar. But the thing with an ester is that they do not form hydrogen bonds. So they don't have any hydrogens on them that are slightly positive, unlike a carboxylic acid. So again, we'll draw out this carboxylic acid. This has 4 carbons. So what they're doing here is we're showing you that these are functional isomers, that both of these molecules have the exact same chemical formula, which means that their dispersion forces are the same. Okay, so dispersion forces are the same only if they have the same chemical formula. Okay, so we'll just say equal, meaning that they're all the same. But again, here with my carboxylic acid, I have a dipole running through the carbonyl. I have a dipole running through the hydroxyl, but I also have this little hydrogen being positively charged. And this is really impactful, right? Take a look at the difference in boiling point just from that little hydrogen bond that is there. So esters are good in terms of polarity. And again, they'll have higher boiling points than any kind of alkane, but no hydrogen bonding present.